Good morning, all. So, in today's lecture, we'll be discussing Smith chart. As we have already discussed about the various parameters that are supposed to be studied in transmission line. So, now we will study the Smith chart, a graphical method to solve the problem based on transmission line. So, we have learned what is a reflection coefficient, what is a transmission coefficient, then what is input impedance, what is characteristics impedance, what is VSWR. All this parameter we have studied. So now, and we have also derived the various expression to solve the problem and to find this factor like tau or VSWR or input impedance, right? So now the same thing we'll be performing using a graphical method, Smith chart. So let us first understand what a Smith chart is. So this is the Smith chart. I already shared the PDF with you. So during the lecture, please look at the PDF I have shared to you. Better you have a printout of this and you can observe the things on the printed version of this Smith chart. Fine. So what you observe on the Smith chart, there are the circles. So some are the complete circle and some are the semicircle. So let me annotate. So you can see these are the complete circle. Like one I am marking here, right? A complete circle. Then these are the complete circle. It will be completed this way because it's under this window. So one can observe the different circles which are complete here. Okay, as what I have shown you. The circle cannot be drawn on this. So these are the complete circle which you find are present on the horizontal axis like this. So the meaning is all the circles are present along the horizontal line. So this is the horizontal line. You can observe this horizontal line. So it is becoming the part of this horizontal line is acting as a diameter for different circle. Okay. Now what are these circles? These complete circle which are starting from this, these circle represents the uh, resistance part. These are the resistance circle. We will call it as R circle. Okay, these are the resistance circle and it is used to represent the value of resistance R. Similarly, you can find the other type of circle which are semicircle like this. One can find here any number of semicircles are given here. So you can just see this arc. Different arcs are present. You can trace anyone to observe it. Okay. So what these semicircles are representing? These semicircles are representing reactance X. So this is representing resistance or impedance and this semicircles are representing the reactance. Now you will find the semicircle present in upper half and in the lower half as well. You'll find here also in the lower half also such kind of semicircles are present. You can consider it. So these are used to represent the plus or minus, positive or negative. type of reactance. So if your reactance is plus, you have to represent using the upper portion of semicircle, and if its value is minus, you can represent using lower value of semicircle. Okay, so have you understood what are these circles representing? Resistance and reactance. Okay, so you can show the total impedance in terms of resistance and reactance, and that can be represented using the complete circles and semicircle. So this is what the circles are representing. Now I will clear this drawing and I will show you the complete Smith chart. So you observe how the Smith chart is. This is the complete Smith chart, right? Now if you observe this, all this is axis, the horizontal axis. What is written there? Can you observe these values? 50, 20, 10, 5.0, 4.0, 3.0, 2.0. Right here it is becoming 1, then it is 0.9, 0.8, 0.7 up to, and the last is, this is 0.1, so it will be 0. These are the value of the resistance of this circle. So if you are tracing a circle of 0.7, it means your R value is 0.7. If your point is present on this circle, so your R value is 0.6. So whichever R value you are supposed to find, you have to show it on this circle. Now, what is the condition? Here R is equal to 0 at this point. Here R is equal to 0. And if you see this side, it's maximum, and towards this your R is going to be infinite. Okay, value of this value is going to be infinite at this other end. So when the condition is R is equal to 0, resistance is 0, and when the condition is when R is maximum, so you can have two conditions of this transmission line, or you can have two conditions of the load. One where it's called as a short circuit. R has become 0. Impedance at the load point is becoming 0. It means it's a short circuit condition. R is becoming 0. It employs a short circuit condition. Okay, it's a short circuit condition. So if you see the extreme left side, so here your R is becoming 0. Here R is becoming 0. That is ZL, load impedance is becoming 0. Okay, load impedance is becoming 0. It means it's a short circuit condition. Similarly, if you see the extreme right end, where it is tending to become infinite, it's a open circuit condition. This indicate that infinite impedance at the load point, which means the open circuit condition. So now remember, R equal to 0, the extreme left side implies short circuit condition, and here at the extreme right side of this circle, it employs the open circuit condition. When you move along this Smith chart, and you have a complete rotation, you have one complete rotation. So if you move and you complete one rotation, it means 360 degree. Okay, 360 degree. Remember, you cover a distance of lambda by 2. Okay, when you complete the rotation of 360 degree on the transmission line, you cover the distance of lambda by 2. So in order to cover the distance equal to lambda, that is equal to wavelength, you have to carry two such rotation. means you have to travel 720 days. 360 plus 360, that is 720 degrees on the chart, so as to cover a distance of lambda. Okay, are you getting my point? When you complete one rotation, that is when you move 360 degree, you actually cover the distance of lambda by 2. And when you cover two such rotation, you cover the distance of 700 and sorry you cover the distance of lambda, which corresponds to double rotation, that is 720 degree. So one rotation of 360 degree corresponds to covering the length lambda by 2. Two rotation which corresponds to 720 degree, it employ the length equal to lambda. Clear? Okay, so now how to find this? Again, I will enlarge this Smith chart. And if you see on this, the last circle, see here, this circle is your r equal to 0. This is the last circle, r equal to 0. Then you find 1, 2, 3, and 4 circles, and something is written in that. So what is there? Some angles you can find 170, 160. Some numbers are given, and these are representing the different angles. Now you see here some arrow is shown. It means when you are moving in this direction, you are moving towards the generator. So this is wavelength toward the generator, right? Signal moving to the generator. So this direction indicates movement towards the generator, and opposite, if you see, it is movement towards the load. In the transmission line, you know, you have a load, you have a source and you have a load. This is source, this is load, and this is the transmission line. So when you are moving towards the generator, source means is a generator. If you are moving towards the generator, you are moving along this side, right? And when you are moving towards the load, okay, it means this is the direction of signal transmission towards the load. It means on the Smith chart, it is shown like this. Opposite of that, clockwise, this is clockwise, this is anti-clockwise. So look here, it is mentioned here, towards the load, moving towards the load. This is moving to the generator. So this implies movement to the generator, this implies movement towards the load. Now how to solve the problem using Smith chart? So let us take a problem and solve it. Okay, so basic things I have shown you, what this circle implies, how to move towards the generator, how to move toward the load, and what does this number implies. Okay. Similarly, on the semicircle also, if you want to observe the value, you can see here, like I will enlarge. If you are moving along this semicircle, here 0.4 is written, here 0.5 is written. Okay, if you want in between these values, so you can select the appropriate semicircle. Okay, so at the end of the semicircle also, its value is given. At the end of this full circle, its value is given, that gives the value of your r, and this semicircle gives the value of your xc reactance. Okay, now let us take a problem and we will solve it, and I will try to show the same things. I have marked it on the PPT, and I'll also try to show here. Now let us take a problem here. Instead of whiteboard, now I will use this. Now let me write the problem and you try to understand. We have already learned how to solve this using theoretical method. Now today we will see method of finding those parameter using Smith chart, that is a graphical method. So let's take one problem. A lossless transmission line. What type of line it is? A lossless transmission line. A lossless transmission line with Z0. What is Z0? Z0 is our characteristics impedance. So Z0 is equal to 50 ohm. What is the characteristics impedance given? It is 50 ohm. So the lossless transmission line with Z0 equal to 50 ohm is 30 meter. What is this 30 meter? It is the length of transmission line. So the line is of 30 meter long and operate at 2 megahertz. And operate at 2 megahertz. Okay. The frequency of operation is 2 megahertz. The line is terminated with the load. Line is terminated with the load. Remember the Smith chart problem, they are asked compulsory. It is there in the paper for 10 marks. So in MCQ, you can expect the question minimum of 10 marks on this unit. So the line is terminated with the load ZL. So I am writing here the load impedance ZL as 60 plus J40. 60 plus J40 ohm. Fine. If U is equal to 0.6 C, C, you know, it's velocity of light, on the line, find what you have to find. Number one, reflection coefficient. Number two, standing wave ratio. Number three, input impedance. So this is the problem given. The problem is line is a lossless line. So a lossless transmission line with characteristics impedance Z0 is 50 ohm is 30 meters. So length of line is 30 meter long and operate at 2 megahertz. The line is terminated with the load Z equal to 60 plus J40 ohm. Okay. So if U equal to 0.6 C on the line, find the reflection coefficient, standing wave ratio and input impedance. Okay, so let's solve. Now we have learned the theoretical method to solve this. Okay, so what we will do first, we will learn the graphical method and then we will learn the theoretical method, because for theoretical method I'll be using whiteboard, so this screen data may be lost. So better I'll first explain how to solve this problem using Smith chart. Now everybody is supposed to have the hard copy of this, a scale, you can have a protractor and a compass with you. Okay. So what is given is ZL. The load impedance ZL is given. So first stage, let us try to find the reflection coefficient tau. Okay. Let's try to find reflection coefficient tau. Yeah. So first of all, we'll try to find tau. What is tau? Reflection coefficient. What is the value of tau theoretically? Tau is equal to ZL minus Z0 upon ZL plus Z0. Okay. Reflection coefficient theoretically can be calculated as load impedance minus characteristics impedance divided by load impedance plus characteristics impedance. Similarly, you can find VSWR. Once you find tau, you can find VSWR theoretically as 1 plus mod of tau upon 1 minus mod of tau. Right? Then you have the formula of Z in. What is Z in? Z0 into bracket ZL plus J Z0 tan beta upon Z0 plus J ZL tan beta. So all these formula we have already done. So now let us see how to find graphically. So first of all, we will find graphically, then we'll solve theoretically, and then we'll match our results whether both are same. Okay. So the first step, using the Smith chart, if you want to find the let's say reflection coefficient first. So first of all, what is given to you is the load impedance. Okay, so normalize the load impedance. So first step is you normalize. Normalize the load impedance. Now, how to normalize load impedance? So, and why to normalize? Because on the Smith chart we have limitations of the numbers. Okay, so we will bring all on the scale what or the values that are given on the Smith chart. So let's normalize ZL. How to normalize ZL? ZL is given to you. You divide the ZL, that is load impedance, by characteristics impedance. So whatever load impedance is given, ZL, let's normalize, and I will call the new load impedance ZLN. That is normalized. And how to normalize it? The given load impedance ZL divided by the characteristics impedance of the line Z0. Now what the load impedance is given to you? It is 60 plus J40. Okay, so I will write load impedance as 60 plus J40 divided by characteristics impedance is 50 ohm. So I'll divide it by 50. It was not possible to show the 60 and 40 circle, no? So that is why we used to normalize it. Okay, so what is the normalized value? If you solve this, it will be, you please use the calculator. So normalized load impedance is 1.2 plus J 0.8. This is what I got. Okay, I have found the normalized load impedance. So my step 1 is completed. Now step 2, locate this. What is the step 2? Locate it now. Locate ZLN. Locate the normalized load impedance. Fine. Now how to locate this? So first of all, now this Smith chart, you please zoom your screen. Okay, because if I zoom, so these things will be misplaced. So you please zoom your screen. Okay, so this is normalized impedance, and it has a real part and imaginary part. So real part is your resistance and imaginary part is your reactance. Okay, so this belongs to R and this belongs to X. So first of all, I want to find R. So I must locate the circle of 1.2. So look here, which circle represent resistance, or these complete circle represent the circle, and its diameter is along this x-axis. Okay. So first find 1.2. This is the center, which is 1, and this, if you observe, if you zoom, you will find 1.2 is written here. Okay, 1.2 is written here. This is 1.4. So at this end your r is going to become infinity, and at here your r is going to become 0, here your r is going to become infinite. Okay, so locate these circle of 1.2. So look on this horizontal axis, where is 1.2? So here it is 1.2. Mark this circle. This is your r circle. Actually it becomes very difficult for me to read it. I'm marking this r circle, complete circle. Perform the same action. Okay, same thing you have to do. So you use your Smith chart, the hard copy, and on that mark this circle. Okay, so we have marked the circle of 1.2. This is my r circle. Okay, this is my r circle. Now mark x circle. Look here, it is 0 plus 0.8. So the reactance circle, they are divided into two parts, the upward and downward. Upward indicate positive, downward indicate negative. So now in my normalized impedance, the value is plus j 0.8. So j circle I am finding on the upper portion. So let us find 0.8, locate. So this is 3, 2, 1.6, 1.2, 1. I want 0.8. So where is 0.8? Look here, this is 0.8. Have you seen? This is 0.8. Okay, so I'm going to again reduce it. I got it now, 0.8. This is my 0.8. The things are got shifted. The moment I change this, the things are got shifted. Okay, this is correct now. So this is our 1.2, and I want 0.8. So this is 0.8 circle. Right? This is 0.8 circle. So you again complete this. Okay. Now find the point of intersection. So you have drawn this J 0.8 and X, and this circle is 1.2 for R. Now find the point of intersection here and call this point of intersection, let's say P. Okay. This is your point of intersection P. Now further what to do? You have to join this point with the center or origin. So join this point. This is the center. This is your x-axis where there is 1, that is the center of the Smith chart. So I'll be joining this line with point P. Okay, I have joined this line. I have joined the center with point P. Okay, got it? And I'll call this as, this is O, center origin, and this is P. So OP, line OP. So draw line OP. Okay, line OP. Then further what I will do, I will measure the length of this line OP. So you please use a scale. Okay, use a scale, and I'll try to show you. Use the scale, okay, and put it at the center. Please zoom this window. And measure the length of this OP on the Smith chart. Now, if somebody is having the compressed version of this Xerox, or somebody is having enlarged, your value may differ, but result will not change. Okay? So this way, please draw the line. Okay, draw the line and call this line as OP and measure the length of this line. So here on my graph, this length of line OP line is coming to be 3.2 centimeter. Then next, what I will do, I will extend this line. I'll draw a new line now. Once you have measured, you draw a new line such that the same, you have to extend it such that it is touching to the last circle here. Last circle is R equal to 0 circle. No, this is R equal to 0 circle. So this line shall touch to this. And I will call this point as OQ. This is Q. Let's mark it by red or different color. This is point Q touching here. This is origin and this is point P. First of all, you have measured the length of OP. Now you measure the length of OQ. The length of OQ I got is 9.1. In the same fashion, put your scale here and measure the length of line, and I got it as 9.1 centimeter. You may get different values depending on how much enlarged version of what is the version of Xerox you're using, whether it's an enlarged version or compressed version. So don't worry, but final answers will remain same. Now, once you have done, you can now find the reflection coefficient tau. So reflection coefficient tau can be finded as the ratio of length OP divided by length OQ. Okay, very simple. If you use a theoretical method, you have to find ZL minus Z0 upon ZL plus Z0, means you need to make some calculation. Here you simply find this normalized impedance, locate point P, measure the length of line and the ratio of OP by OQ. That is, in our case, it is 3.2 centimeter divided by 9.1 centimeter, and it comes to be 0.3516. So how much is your tau? Tau is equal to 0.3516. This is the reflection coefficient you got. Clear? How to find tau? First of all, take the load impedance, then normalize it. Okay, normalize it. After normalizing, locate this R on the complete circle, locate this J value on the semicircle. If J is positive, use the semicircles on upside. If J is negative, use the semicircle of downside. Okay. So this way you have find it tau. Now let us find SWR. So second part we will find is standing wave ratio. SWR, or you can say voltage standing wave ratio, whatever. So standing wave ratio. Now how to find? Again, this is very easy. You have located here point P. Just a minute. So what to do? First, draw a circle. Now what shall be the radius of that circle? OP. OP shall be the radius of that circle. So you must draw a circle. Now you use your compass, put its center here and mark your pencil here. Take this distance and draw a circle. So I will try to show this circle. I want this radius now. So roughly I will first plot. It will not come exactly if I find it roughly. You should draw a very precise circle. You cannot drag it. This is perhaps better. So you have drawn the circle. You have drawn this circle. So what you have to do, take the distance of OP in a compass and draw a circle. Now this is not a very exact, very correct circle. Uh, I can show you on the PPT. Yeah, see, this I have drawn. So I will share this after. So once you find this circle, you see this circle is intersecting this horizontal axis at two sides. One is here. Here it is intersecting and here it is intersecting. Now the center is R equal to 1. To find VSWR, you have to consider the right side where R is greater than 1. So consider R greater than 1 side. Then find the point of intersection. So this is your VSWR circle. What is this? VSWR circle. Now this VSWR circle is intersecting here. What is the value? Uh, if you draw this circle very correctly, it will be like this, and it will intersect at 2.1. Okay, so you please draw the correct circle, and this is your r greater than one side, and this is your r less than one side. So towards this r greater than one side, see where it is intersecting. So now in our case, it is intersecting to the circle 2.1. Okay, so SWR is equal to 2.1. Simply note down the value of this r where this circle is touching. Okay, so it will be 2.1. It may be like this. Okay, so if it is intersecting here, if this value is 2.1, so you note down this value, that is intersection circle. So that is the value of your SWR, standing wave ratio. So tau we have find it, standing wave ratio we have find it. Third, we have to find input impedance Z in. Okay, input impedance Z in. So now remember, very important, how to find input impedance Z in. So to find Z in, first express the line length in terms of degree. To find ZL, express the line length in term of degree. Now what is this? I will explain you. So first of all, you have to find what is lambda. Find the wavelength. What is wavelength? We have seen, we have derived this. So wavelength is equal to u by lambda. Sorry, u by f. What is u is given to you? Velocity 0.6 into c. Okay, so this velocity is 0.6 into c. 0.6 into value of c is 3 into 10 raised to 8 meter per second. So it will be 0.6 into 3 into 10 raised to 8 divided by what is the value of frequency? It is given 2 megahertz. So let's write 2 megahertz here. So 2 into 10 raised to 6 hertz. What comes lambda? If you solve, you will get lambda is equal to 90 meter. So for this signal, the wavelength is 90 meter. Okay. Now what is the length of line? Length of line is given 30 meter. Okay. Length of line is given 30 meter. Just a minute. Yeah. Length of line is 30 meter. Now let us find this length of line in terms of lambda first. So if 90 is your lambda and 30 is your length of line, so how I will express line length in terms of lambda? So you find this length of line in terms of lambda can be finded. What? How much is the length? 30 meter. What is the lambda? 90 meter. So it is equal to 1 by 3 of lambda. what we have done, simply the length of line which was given 30 meters. So this 30 meter I have expressed in terms of lambda. So if lambda is 90, so what I can say, length of line is lambda by 3 म्हणजे 30. 30, I have expressed 30 in terms of lambda. So lambda corresponds to 90 meter. So given length of line is lambda by 3. Got it? So first of all, write the length of line in terms of lambda. Now, you know that when you complete one revolution around this, that is 360 degree, you cover half wavelength. Okay. And when you complete two revolution, that is 370 degree, you cover one wavelength. Okay. So to cover the distance of lambda, lambda corresponds to angular movement of 720 degree. Have you understood it? How much is the angular moment? When you complete 360 degree angular moment, you cover lambda by 2 distance. When you cover two such rotation, that is 720 degree, means you are covering wavelength lambda. So lambda corresponds to angular moment of 720 degree. Okay, fine, got it? So now what is the length of line is lambda by 3. Now in terms of this, how much it will this length will cover in angular? Lambda covers 720 degree. So lambda by 3 covers how much? 240, right? 240. Lambda corresponds to angular movement of 720. So lambda by 3 corresponds to 240 degree. Is it clear? Okay, let's move further. So just divide it by this 3. This is your lambda divided by 3. It's a 240 degree. I will write here precisely. Lambda corresponds to 720 degrees. Therefore, lambda by 3 corresponds to 240 degrees. Now, that means we have to move towards the generator by 730 degree. Sorry, 740 degree. Okay, this is your point P. From point P, which is the direction of movement towards generator, this is the direction of movement towards generator. Okay, this way. It means from this point I have to cover a distance of angular distance of 240 degrees in the clockwise direction. Okay, so now and where? On this S circle. So move on this VSW or circle by angular movement of 240. So it is very simple. Now you see here what is the angle. Yeah, one thing I forgot. You have measured tau. You have to find the angle also. Okay. So here simply you have to either you use a protractor to measure this angle AOP, or you just simply extend this line here. Simply extend this line. Okay, you will find here the angle is written. Now, if I zoom again, it will change. And because I have drawn it by hand and then rotated, so things are changed. But you can see this is 40, 50, 60, right? Actually, this line comes up to 56. Okay, so this is not, if you draw this line, so it will come up to here, like it will come up to here, and between 60 and 70. Okay, right now it is, if you zoom, this line will come at 56. You see this, I notate and show, measure what angle is given here. So where this line intersect, because of zooming of this, I'm not able to focus, but right now it is showing here to 72. But if I reduce the screen, then it will be changing. So if you see the actual thing, it will be 56. Now, on this screen, it is showing now, but it has shifted. Uh, this is showing something else because it movement is not accurate. So measure what is written here at this point, and it will be 56 degree on your paper. Okay, so you please, whatever is the length, you will get the same angle. So angle comes to be 56 degree. Fine. So for you have to find the angle for reflection coefficient. Okay, coming back to the input impedance. So you have finded what is lambda. Then you have represent the length of line in terms of lambda 1 by 3. Then you have converted the length of line into angular distance. So it corresponds to 240 degree. So move your point on this VSWR circle. This is your VSWR circle. So move from this point to make a rotation of 240 degrees. So if you go exactly opposite to this, it will be 180, and further you cover the remaining distance. Okay, this will be 180, then 190, 200, and up to 240. So 60 degree again you move. So how you will find this? Not able to show. Okay, I'll show another video. I'll show it on the same thing. I will show you on PPT. So you can measure this angle, or simply you put your protractor, measure 180 degree, and from here measure remaining 60 degree. So 240 degree you have to make the angular movement. After doing this, you will uh, get the point somewhere at on the VSWR circle. Locate the point. Locate that point where it completes. So suppose if I take randomly, it will be 180 degree. Then from here I have to measure 140. So somewhere around this. So this distance shall be 240 degree. total. Then you get a point, mark this point, and at this point you find the value of z in. Okay, so at this point, what is your full circle and what is your semicircle that are passing through this? So find the value of this full circle, that is resistance circle. Note down this value on x-axis. Okay, so that comes to be 0.3 in actual case. So this will be 0.3 for r, and which semicircle is moving? So you will find 0.63. The semicircle which is moving from which is crossing this is 0.63. So then I can write z in at that point. This was your VSWR circle. This was VSWR circle. Somewhere on the VSWR circle, let's say this was your point P, and then you moved from this point till you cover 240 degree. Let's say here you have covered 240 degrees from this point. Okay, and then find what is the value of r here and what is the value of the semicircle which is passing through this. Okay, so this is your z in. Okay, of course this is your normalized because initially you are normalized. So value of z input impedance, you have to find input impedance, right? So you are moving towards the generator. Okay, so z in is equal to, it will come, value of r will come 0.3 and value of x will come, so I will represent it by j 0.63. So this is your input impedance, but this is the normalized because initially your load impedance was normalized. So from that load impedance, using graphical method, you have finded the input impedance of the line. Now I will unnormalize it. Okay, initially you have divided the load impedance by z0. Now I will multiply z in by z0 to z in, normalized by z0 to get actual z in. So what was our z in? Characteristic, our characteristics impedance was 70, and this z in is this. So 0.3 plus j 0.63 multiplied by 75 ohm. So what I will get is 22.5 plus j 47.25 ohm. So this is your Z in that you have simply find it from the Smith chart. Okay. Now whatever values you have finded, you can cross check it. Okay, you can cross check it. Okay, so let's cross check with the help of theoretical method. So theoretically, let's find tau. So what is tau? ZL minus Z0 upon ZL plus Z0. What was your ZL? It was given to you as 60 plus J40 and Z0 was 50 ohm divided by 60. Just this is ZL minus Z0, so it should be minus. So this will be 60 plus J40 minus 50. It will be plus. So this will be 60 minus 50 will be 10. Correct? 60 plus J40 is your ZL. 60 plus J40 is your ZL. So minus 50 here and plus 50 here. So it will give you 10 plus J40 divided by 110 plus J40. Okay, so if you calculate, you put your calculator in the polar mode. So find, you can simply shift your polar button and then press equal to. So you will get the answer of for this ratio 0.3523 at an angle of 56. Again, if you press shift and equal to, you will get the angle of this. Okay, so tau you will get exactly similar as what you have find it in the graphical method. Second, you have to find VSWR. Okay, that is voltage standing wave ratio indicated by S, that is given as 1 by magnitude of tau upon 1 upon tau 1 minus tau. Okay, so tau you have find it here. So let's do the addition. 0.3523 and divide this is 1 minus 0.3523 and it will give you 2.088, and what you have find it using graphical method, that was 2.1. Okay, so approximately, or it is almost same. Then third, you have to find the input impedance. So for finding input impedance, you know what is the formula for input impedance? Zin is equal to Z0 into bracket ZL plus JZ0 tan of beta L divided by Z0 plus JZL tan of beta L. This is your input impedance. So for this you need to find beta L. Okay. Now to find beta, you know what is you omega by beta, or you can say beta is equal to omega by u. Okay. Therefore, you can say beta L, beta multiplied by L is equal to omega upon u into L. So I'll use the next this beta L is omega L divided by u. That is, what is your omega? Frequency is given as 2 megahertz, so it will be 2 pi f, that is 2 pi 2 into 10 raised to 6, and length of line is given as 30. Value of u is 0.6 into c, that is 3 into 10 raised to 8. This comes to be 2 pi upon 3, which is equal to 120 degrees in angle. Okay. Now, this is a lossless line. That is why we have written Z in for the lossless line. Now you put the values in the equation of Z in. I'll rewrite here. That is equal to Z0 into ZL plus J times Z0 tan beta L divided by Z0 plus J into ZL tan beta L. So Z0 is 50. Put all those value. Your load impedance is 60 plus J40. plus Z0 is 50, so it will become J50 tan of beta L is 120 degree. Just now we have calculated, divided by 50, again Z0. So this is 50 plus now J times ZL. So ZL is 60 plus J40 tan of 120. Okay. So if you solve this in the polar mode, you will get the answer 24.01 at an angle of 3.22 degree in the polar form. And in the complex also, in the complex form also on your calculator, you can find the answer in the complex form. It will be 23.97 plus J 1.35 ohm. So this way you can solve and tally. Now the next question comes here, how to find the maxima and minima using the switch chart. So that we'll discuss in the next lecture. Okay, so we'll stop here today.